This video is part of a course on food physics. It is the first one in the series of videos on food modeling framework or food physics frameworks, just the theory part of it. It is the easiest one, but an important one as it paves the way for more complex ones to follow. So there are many ways to understand food physics, many different levels, and many ways to model it. It's from the simplest to the most complex. Lumped parameter is pretty much the simplest. It's on the low end, lowest end of the mechanistic modeling. If you think of the entire range, there's nothing simpler than this. And it's also not very widely applicable because of that reason. Then why study it? Because it actually is a good place to start to understand transport processes, and it is also applicable to a limited extent in some situations. I have divided the video into three parts. First, talk about very fundamental concepts of lump parameter, that's kind of broad-based. Then apply to the heat transfer and derive the equation for heat transfer, and a very similar one for mass transfer. So first, the fundamental concept. Before we get started, how about a little thinking? Just to jog our memory, just to get into thinking in terms of transport processes. So here is a question. Can a lower moisture air, meaning it will be dry air, remove, and by remove I mean per unit area, water just as fast from the thin slice as from a very thick slice? So it's water removal, drying per unit area, and the question is the thickness going to play a role? So with that, you can pause the video and think about it, and then come back to the answer. So the answer goes like this. Initially, air can remove moisture. I'm sorry, there's a lot of text here. Remove moisture at about the same rate in a thin or thick slice, because it's just a question of how fast you can evaporate from the surface. But the surface moisture will go down as it dries. Eventually, removal of moisture will depend on just how fast you can replenish the surface water with inside water. This is harder for a thicker slice because the water has to travel longer distance. So the inside comes into play or becomes important more for a thicker slice or later in the drying process. We'll see why. To understand these transport processes in very simple way, let's try to bring an analogy of transport, not of heat or mass, but people. So let's say I am in the center of this island and I really need to get to here in the water. So it's obviously there are two transport times involved. You first have to get to the edge of the island using a bus or a train or some sort of transportation. And then from here, you need to go to here using some boat or some sort of transport. So these two, you can think of, they're kind of independent. And there are two transport times involved, inside and outside. So we can think of there are two resistances to movement. There's the internal resistance that depends on how fast the bus is traveling, or uh, uh, how the metro is going, and the outside is depends on how fast the boat is traveling, and these are two independent ones. And so let's now bring in heat transfer. So we can think of heat transfer in exactly the same way. So let's say we have this hot object in a cold fluid, then energy, thermal energy from inside has to first come to the surface to be able to cool this solid. But coming to the surface is not enough. It also has to go to the bulk fluid. So again, there is a transport time inside for heat, and there is a transport time in the fluid in almost exactly analogous way. So we can think of there is an internal resistance to heat transfer that depends on what the solid is like, and there is an external resistance to heat transfer. So now let's look at the relative magnitudes of these. There can be three possibilities, right? One is the boat takes much longer than the bus. And the other one could be the bus takes much longer than the boat, and they take about the same time. By analogy, in heat transfer, the heat leaving the solid needs to travel inside the solid and then outside. So there are three possibilities. What are they? One is heat transports very fast inside, and another one would be heat transports slow inside, and the other one would be heat transport in about the same rate inside as well as outside, in exact analogy to the transportation. So in the first case, heat transports faster inside. That means the internal resistance is much smaller than the external resistance. Whereas when heat transports much slower inside, like this one, then the internal resistance is much higher than the external resistance. And the other case is there about the same. So this lumped parameter has to do with this situation, that internal resistance is much smaller than the external resistance. In other words, heat can travel from inside to the surface much easier compared to how fast it can get out. Let's look at a few practical examples in the food area of this concept. So the first one I have is for heat transfer, and the two examples the first one is temperature of leaves. Just leaves are thin, being dried in hot air. So if the leaves are thin, then what will happen is there is it doesn't take much effort for heat to come from inside, very deep inside the leaf to the surface, because the distance is very short. So the internal resistance then is small to heat transfer. Another example is thinking of the average temperature of fluid in a can that's being agitated. So if the can is being agitated, so the contents are being mixed very well, then the what's happening is the mixing reduces the resistance between deep inside and the surface, because this resistance, it doesn't take heat much effort to go from inside to outside because it's all being mixed. So mixing reduces that resistance, and then So the internal resistance is small. So both of these cases, internal resistance is small compared to external resistance, or can be small. And these are examples in heat transfer. Now we look at two examples of this internal resistance being small in mass transfer. So drawing of a thinly sliced potato. Because it's thin, the moisture from inside, if this is my cross section, it's thin from inside to the surface. It doesn't uh, need to make that much effort. So internal resistance is small. Another one would be some fluidized bed drying, meaning the these the corn, it's not drying all in like one big uh, amount, but individual kernels. So which means heat only, or the moisture only has to move this distance, a small distance, compared to if many of these grains were together. So in this kind of drawing, then the internal resistance could be small. Now, generally, this assumption is not valid over most of the drawing time, and we'll get into more details later. But here are two examples that we can possibly try to relate to this concept of small internal resistance compared to the external resistance. So, in terms of a very general statement, this kind of a assumption that we're going to develop more details of the equations later, this assumption does not work for most of the realistic situations. Um, so, in other words, ignoring the transport time inside compared to the outside, it doesn't work most of the time. So, in case of drying, for example, mass transport is often slower inside. And so these two are the more realistic situations, the two that we are not doing here. So this chapter is about the first one, but I am saying we have to be very, very careful how few cases we can really apply, because most situations the mass transport, for example, is slower inside. So you're more often limited by what's going, how slow it is inside. So this assumption that we have in this chapter that we can ignore the internal resistance is not that realistic, but it still is applicable in some situations. We will now get into building the detailed equation for lumped parameter in case of heat transfer. It's actually a very simple one. So to derive the equation for temperature in case of heat transfer, I'm going to uh, think of like the leaf, for example, is very thin. So I can think of the entire material as in one temperature. So entire material is like a lump, and it is at one temperature. That's the temperature of the entire solid, and the fluid flowing over is at T infinity, which is a different temperature. So we ignore any spatial variation inside the solid, and what we do is we apply the law of energy conservation. What energy coming in minus energy coming out plus energy generated is equal to the change in storage of the energy. Now let's put in the quantities. So suppose this is a situation where the solid is warmer. So if the solid is warmer, then it's going to lose heat. So in part is 0, And energy convected away, H is the heat transfer coefficient, which has an unit of watts per meter square per degrees Kelvin, times area meter square times degrees Kelvin. So these all cancel out. So we get watts times seconds. This one gives me joules. So the unit for this entire amount is joules. So that's how much joules that have left the solid. So it's out over this time period delta t. And for now, let's consider no generation. So generation is 0. And because energy was lost, there's going to be change in storage, or there will be a change in uh, temperature. So, so the change in storage is mass times specific heat times change in temperature delta T. So simplifying, we write del T over del T is equal to HA over MCP, these two together, times T minus T infinity. Okay. So if I let now the del T go to 0, and so that del T also goes to 0, then we can write in terms of a little differential equation dt dt, and to solve that, of course, we need the boundary condition. So then this is our governing equation, this is our boundary condition, much too simple, but that's what defines a lumped parameter model, or that is how we do the lumped parameter analysis. Notice that it is not empirical in any way. It has the physics built into it. Although these series of videos are more for setting the framework and not exactly solving those equations, because the equation solving would happen later in applications, in individual applications. So we're not typically solving the equations, but in this case for lumped parameter it's just too simple. So uh, why not we just go ahead and solve it? To do that a little more organized way, let's define theta as t minus t infinity in the equation from the previous slide. So if I do that, then our governing equation gets transformed into this one, which is very simple, of course. And to solve it, we bring the thetas on one side, so d theta over theta, and t on the other side. These quantities h, a, m, c, p, t, they are all constants, and I changed the limits. It was ti before, so now it's theta I, where theta I is simply ti minus t infinity. Um, so if we go through the solution, of course, first time if we integrate, then we get log of natural log of theta with these two limits, theta I and theta, we get natural log of theta over theta I is equal to the right hand side, um, okay, which means we can write theta over theta I as e raised to minus ha over mcp t, and we can rewrite that slightly, and we'll see why. So first is I substitute for theta t, so we have t minus t infinity over ti minus t infinity, and e raised to minus t over mcp over ha. Now we can think of this mcp over ha as one kind of one quantity, and it actually has a physical interpretation. It is kind of the time constant, and it will be clear in the next slide. But for now, then our solution is this one, temperature as a function of time. Note, it is not a function of position, because we're saying this entire material we can think of at one temperature. In other words, there is no resistance inside. To give the analogy, it takes no time to come from the center of the island to the surface, or it is very easy for heat to go from the deep inside to the outside. Um, so that's the case that we are just solving. So now we try to understand the solution. So the solution that was t minus t infinity over ti minus t infinity is equal to e raised to minus t over tau, where tau is mcp over ha. If we plot this one, which is always useful, so temperature T plotted over time, it starts from Ti and it approaches T infinity. It approaches T infinity, never really reaches T infinity. And let's look at the solution a little bit more. So as I said, this mcp over ha is time constant. And what is the meaning? Why is it called time constant? So let's say for t equal to tau, so at a value of t equal to whatever this value time constant is for a particular situation, at a value of t equal to tau, t minus t infinity over ti minus t infinity is equal to e raised to minus 1, which is, just 1 second, is about 0.368. So if you simplify this expression, you'll see that t is equal to ti plus 0.632 times t infinity minus ti. This is a little bit of massaging of these numbers. So this is the temperature. So what this means is when t is equal to time constant, so this is my time constant, t, tau, equal to mcp over ha. At time constant, the temperature has changed to 63.2% of the total possible change. So the total possible change is this. This is the total possible change. 63% of that has happened. So 63% of the total possible change means the actual temperature is Ti, it starts from plus the 63.2% change, and that gives the temperature at t equal to tau. So at time so the meaning of time constant is 63% of the total possible change happens during this time constant. So if this value mcp over ha is smaller, then the 63% change will happen in less time, which means temperature is changing faster. So in these two cases, this one has a lower mcp over ha. So the temperature change is faster. And lower mcp over ha happens when h is higher, or there's more surface area, or lower mass, or lower specific heat. Okay, So that's the understanding of this lump parameter, that we have temperature versus time, and, that temperature versus time still depends on these physical quantities, the mass, the specific heat, the uh, the heat transfer coefficient outside, and surface area. Note, we don't have any thermal conductivity because the conduction inside is ignored. It says it's fast enough because the material is either very thin or highly conducting or so on. Okay. Then this is our lumped parameter equation that says how temperature changes with time. And it's a very, very simple equation. And so then it would be nice to be able to use it all the time. But that's obviously not the case because we derived it making some very major assumptions. So what are those assumptions? We said that there is no internal resistance, meaning heat conduction from the center to the surface is fast enough, either because it's very thin or it's highly conducting and so on. So that's a huge assumption that we are ignoring all of the resistance inside. So we're saying temperature can quickly equilibrate and there is only one temperature. So when so this small internal resistance, it's nice to say it's small, but we have to define what is small. So let's do that now. So for a slab, taking slab as an example that's being heated from both sides, and the slab having a thickness of 2L, uh, we're saying internal resistance has to be small. So internal resistance over external has to be small. So for a slab, the internal resistance is L over Ka, and external resistance, convective resistance, is 1 over Ha. That gives us HL over K. That has to be small. So it turns out that if that is less than 0.1, then you can think of it as small. Again, these resistances are inside it's the conductive resistance L over Ka, and outside it's the convective resistance, and this ratio HL over K is called the Biot number. If it is less than 0.1, it turns out this simple solution, this one, can give temperatures that have less than 5% error. So if this condition is satisfied, then the error is less than 5%. That's the limitation of using this lump parameter method in case of heat transfer. Now we apply the lump parameter concept to mass transfer situation. It's actually quite analogous to the heat transfer that we just did. We now develop the lumped parameter equation, or one of the lumped parameter equations for mass transfer, following what was done for heat transfer in a very analogous way. So we ignore any spatial variation. So let's look at a process like drawing of this. Let's say this is like a potato slice, and we are flowing air, dry air over it to dry. And the way we want to think of is that we ignore any variation of moisture inside. And so the material is like a lump, and it has no variation in moisture from location to location. That is, of course, not true in general, and we'll come back to this. But for now, that is the assumption of lumped parameter. So this material is at a moisture content W, okay, and then we just want to do a mass balance, just a conservation of mass to try to see get an equation for W as a function of time. And the dry air that is flowing, it has a concentration of water vapor as C infinity, and Cs is an interesting one. It is the moisture in air at the surface that is in equilibrium with the water in the solid. We'll spend more time on it, but it's the value in air. It's not the moisture content at the surface. It's the value in air. So let's do a mass balance. And we say mass in minus out plus generation equal to change in storage. And in this case, if it's a drying process, then it's losing water. So let's write how much it lost over some time. So if ms is the mass of dry solid, so let's say this is kilogram of dry solid, and W is the moisture content, kg of water per kg of dry solid. So then del W would be that this times kg water per kg dry solid. So these two cancel out, and so the unit for this is simply kg of water lost. And so how did it lose? It lost because it's losing from the surface. The moisture is evaporating at the surface and it's being carried away by convection. How much, at what rate is it being carried away? So because it's drying process, of course, things are not coming in, and the amount that is carried away is the mass transfer coefficient, and if we put the units, maybe it would be easier, meter per second times area is meter square times concentration of vapor at the surface. So this is again, we need to be very careful. It's not the concentration of water in the solid at the surface. It's concentration of vapor at the surface in air. And then C vapor infinity is the C infinity concentration of vapor in the bulk air, so far away from any effect of this solid. Okay, and so the concentration difference, then the unit for that is kg per meter cube. Okay, kg of water per meter cube. And so these cancel out, so we get kilograms per second times the over time delta T, it's seconds, so it's kilograms of moisture that is lost, and that's equal to this on the right hand side. So now we simplify this equation and also we algebraically simplify, but we also make del T go to 0, so we get a differential equation. So we get dW over dt. Let me wipe the old stuff out. So dW over dt is equal to this quantity, and that is my differential equation for lumped parameter. In case of mass transfer, it's one of the possible ways of writing. You can see it's way too simple, and so we have to pay a lot of attention to when we can use it. So you notice there are problems. So first is that it's missing all the detailed mechanisms. We're not talking about how moisture gets to the surface and so on. And then some more detail, uh, we are ignoring, so suppose there's pressure driven flow. If this is being heated really at high temperature, there's going to be vapors generated inside and it could generate pressure. And so that pressure driven flow we are ignoring. Then even diffusional limitation, moisture has to diffuse. It needs some time, it needs some effort to diffuse, and we are ignoring that one. We are not even talking about the thickness, which is part of the diffusional transport. We're ignoring that. And there, if we are heating this up, or even if we don't want to heat up, there's going to be some temperature variations across this. Maybe small, but we are certainly ignoring that. And also there's evaporation that we are ignoring. So if we ignore all of these and we make these very gross assumptions, um, then we can write this equation for lumped parameter analysis in case of mass transfer. So now we have this differential equation for lumped parameter analysis in case of simple mass transfer, in case of drawing. So it's W as a function of time, and it's an extremely simple equation, but we treat it even simpler by making this assumption, treating the right hand side to be constant. Why? So this we really have to understand so that we use this equation properly. For this to be constant, of course, all of these are constants. Ms is the mass of the dry solid, so that's constant. So let's say Hm, mass transfer coefficient, is constant. Area, surface area, is constant. So if it's shrinking and all, then we have trouble. But this Cs has to be constant, and then the only way Cs is constant, or one of the ways that Cs can be constant, is first it is very wet. So if it is very wet, then the vapor concentration at surface is same at vapor pressure. Okay, so vapor pressure, then the other vapor pressure depends on temperature, right? So this is one assumption. The other assumption is temperature does not change. So if temperature does not change and it's a very wet surface, then the amount of vapor that's on the surface is a constant because it's given by vapor pressure. So then Cs is constant, and C infinity is the surrounding humidity, or in this case kilograms of water vapor per meter cube in the air. And let's say that humidity also does not change. Then we can treat this as constant. And to solve this, of course, we need the initial condition. So we can be more specific. It's just the initial condition. And with that, we solve. So dW at time t equal to 0, we have the initial moisture Wi. At time t, we have W. And because all of these we said are constant, they're outside. And we can perform the simple integration. We see W minus Wi is equal to some constant times time. And so the point is the rate of moisture loss dW dt is a constant. This whole thing is a constant. And that's one of the things that we get to from lumped parameter. So let's look at this in more detail. So this constant rate of drying, so here we're plotting rate of moisture loss. So it's rate, dw dt versus time. And we saw from our equation in the previous slide, dw dt is a constant when we have the surface very wet. So maybe as we are starting the drying process and so on, so the rate is constant. So it's a straight line, but it's not going to stay that way. So this lumped parameter assumption eventually is going to fail when the internal diffusive resistance dominates. So let's talk about this little bit. So eventually we know that that drying rates kind of fall like that. So this material, when it has less moisture, its diffusivity is lower. This is actually not data for food. This is for soil, but it's a representative of porous medium, which we can treat the potato or most of the food to be. So the diffusivity, moisture diffusivity drops sharply. This is log scale, drops sharply with moisture content. So as the moisture gets lower and lower in this same potato slice, then the diffusivity keeps getting lower. And so if the diffusivity keeps getting lower, if this is the slice, then the internal resistance, remember we talked about internal versus external resistance. So internal resistance, if it's for a slab, then it's L over dA. So if D keeps going down, then this ratio keeps increasing. So eventually the internal resistance is going to be so much more that it's not going to be, the process is not going to be driven by just the external resistance, which lump parameter is. And so then at that point the rate would be falling because moisture has to go out from the middle to the surface. So that's a limitation of this lumped parameter, that it is this constant rate, all this stuff can be valid this very early stage in the drying process. Most of the rest of the drying process, you cannot treat this as lumped parameter in most cases. There's a lot of variation with materials and so on. Um, so, so now we have to look at when is it that we can use this lumped parameter analysis. When can we use lumped parameter analysis and talk about constant rate? We take a slab as the example and try to write when is this approximation valid. So this slab has a thickness of 2L, and so for this, remember this lumped parameter is when internal resistance is small compared to external resistance. So let's write internal resistance over external. Internal for a slab, just like for heat transfer we had L over Ka, so here we have L over dA, and for external, instead of uh, 1 over HA as we did for heat transfer, here it's 1 over HMA, but there is also this factor K star that has to do with moisture in two phases, in the solid inside the slab and in the gas outside, that I'm going to do an entire slide explaining in just a second. So given this internal over external, then this is the ratio, and this ratio, again, this diffusive over convective resistance, and the ratio is also Biot number, of course, but it's Biot number for mass transfer. When that is less than 0.1, we can say these simple solutions give concentration that has less error. I cannot say it is less than 5% error because the lumped parameter solution that we derived is not 100% the same as the solution for heat transfer. We can do that also, but we didn't. What I did was the more common lumped parameter equation, and that one is not same as the one for heat transfer. So we cannot use that same 5% error that we said for heat transfer. It should have small error. Now we want to spend some time following what in the world is that K star. K star actually relates to water activity. It has to do with the fact that there's moisture in the solid and moisture in the air. These are two different quantities. They are related, but they're two different. So if we think of this slab being dried, and at some point during drying, this could be the moisture profile inside the slab, which means moisture in the solid, and then this could be the moisture profile outside. You notice that at the surface, we can talk about moisture in the solid or moisture in the air. They're not the same thing. They're related because they are at equilibrium, so they have this kind of a relationship here. So this x-axis here is humidity in air, so this is the sort of the moisture in air, and this is, in this case, the curve is for apple tissue, and so this is the moisture in apple or moisture in the solid. So moisture in the solid and moisture in air, they are related by this. So higher the moisture in air, more is the moisture in the solid, as many of you already know. So we have to make use of this relation here because we are combining in the same problem, we're combining solid phase and fluid phase together. So to keep things consistent, the concentrations need to be in any one unit or other, and that's where the conversion comes in, the K star comes in. So the conversion simply is this: concentration of vapor at the surface and concentration of water at the surface, which are related by this equation, is a ratio. So if we think of, approximating it by a line, then it has to do with the slope of this curve. And so K star comes from the particular material. So it's, in case of food, it's often those isotherms that we know, like the one I'm showing here. So from there, you get K star, which is the relationship between a concentration of water vapor at the surface and concentration of water vapor or concentration of liquid water or liquid plus vapor, everything mixed even in the solid. So concentration of water in the solid, concentration of water in the vapor is the ratio of that. So that K star comes into picture when we talk about the Biot number. So just to conclude, lumped parameter analysis in case of mass transfer goes like this, that if the Biot number here, this one for mass transfer, is less than zero point 0.1, then that simple solution that we derived for concentration is likely to have much less error. But the important part to put things in perspective for practical applications is for mass transfer, the Biot numbers are often large. So this number is often large for mass transfer. So this lumped parameter analysis is often not possible. It may be good for early stages of drawing, but it's for very restricted cases that we can really do lumped parameter analysis for mass transfer. Summarizing the module, internal resistance, which can be conductive or diffusive, can be ignored compared with external resistance, typically convective resistance, under certain conditions. And that condition would be given by what's called Biot number less than 0.1 that we will see in the next slide. But it's only under these special situations that we can ignore the internal resistance. And if we do that, then for heat transfer, we can come up with a very simple equation for temperature versus time. And likewise, for mass transfer, one of the many possibilities of lumped parameter formulation would give me this kind of moisture versus time. So these are very simple descriptions, but they are applicable under very restrictive conditions, which are these. So the simple lumped parameter solution for temperature that we did, it provides a solution that has less than 5% error when the condition below is satisfied. So the condition internal over external resistance given by HL over K should be less than 0.1, and of course there wouldn't be any phase change, there would be no heat generation and all of that. So it's just for the equation that we derived. Likewise, for mass transfer, we can have a similar situation that that can allow us to do lumped parameter. So in this case, this one is very much like the one for heat transfer, except we have the K star. So the K star has to do with relationship between moisture in two different phases of solid and air, explained in detail earlier. We cannot say that when this is satisfied, the solution that we derived also has 5% error, because that solution is not 100% analogous to the heat transfer. But still, this condition should give us guidance on whether we can get away with using lumped parameter for mass transfer. Now, relating what we did to the big picture, we see that there are many ways to describe a food process. So these are all mechanistic descriptions of food process, going this way, more and more detailed and more mechanisms in there. Lumped parameter is here. So it is the simplest. It does help us understanding the transport processes in a very baby way, but important way, and it is applicable in some limited situations. So the lumped parameter models that we showed in this module, they can be improved, and they can be used for maybe they have been used for more complex processes. But when you use it for more complex processes, we cannot talk anything like that 5% accuracy. So the accuracy, when you try to use it for more complex processes, then its accuracy can only be found by comparing with experiment. And for more complex processes, if we use this kind of a lumped parameter approach, it is really tending toward empirical. So there's two examples I want to share where the lump parameter model is improved. So in this one, the researchers included surface evaporation. So when you are heating the product, which is this part, just our regular lumped parameter model, to that you also include evaporative heat loss. So how do you do that? You can actually do the experiment to see how much water is lost, at what rate water is lost. From there, you can find surface water flux. So that will be mass per unit area per unit time, times the surface area times the latent heat. So now you're including the latent heat of evaporation at the surface, and therefore improving this model. And then another example would be uh, microwave heating. So together with the regular lump parameter equation, you can include internal heat generation. And so that will be microwave absorption in watts per meter cube, watts per unit volume, times the volume of the material. So when you do this kind of improvements, they're still lumped equation and they're still somewhat mechanistic. They're simple, but they're still mechanistic. By contrast, there are models that may look like they're lumped parameter, but they're not mechanistic. They're empirical models. And so just to contrast, I have chosen two. One is for retort processing. So the temperature of the product versus time, temperature of the product versus time is given by this equation. And the parameter K is obtained by fitting experimental product temperature. And so this is an example of a completely empirical equation. Another one is a well-known equation for thin layer drawing, and this one called Page's equation. So it gives mass uh, or sorry, moisture changing with time. But um, if n is not equal to 1, then it is completely uh, uh, empirical. It is just a way of fitting the data to get parameters like n and k0. If n is equal to 1, then this equation can come from a differential equation like this: dm dt equal to minus k 0m. So which can look like a lumped parameter equation. So such equations uh, have great utility. Both of these kinds of equations, the two that I'm showing, the empirical equations, have great utility, and they're likely to have increasingly more utility as we, embrace more data-driven model. But they are not mechanistic, whereas lumped parameter is mechanistic. To follow up, what lumped parameter was about is when internal resistance was lower than external resistance. And so it's this case that we did. When we did this earlier, when we started, then we said more realistic case would be these two, where internal resistance is even greater than the external resistance or they're equal. So these are more realistic, as we said. So if you want to know more about these realistic ones, then we go to the next module in a second. If we want more mechanistic description or something that has more details of the physics in there, then in this continuum of physics, from very simple, the lumped one, to the most complex, the next one would be this that has distributed as opposed to lumped. And the next module would get into a lot more details of the physics uh, that is in the internal resistance, which we ignored. Thank you.